Hello everyone, welcome to chapter 3 Moon Phases and Eclipses. So, in the last chapter, we talked about Earth's motion and how it shapes what we see in the sky. Now, we are shifting our focus to the moon, the second brightest object in our sky. So, you will learn why the moon changes shape each night, what causes eclipses, and how these events are not just beautiful, they are predictable. Here are the goals for this chapter. First, we will learn why the moon appears to change shape. That's we call its phases. Next, we will talk about lunar eclipses, where Earth's shadow falls on the moon, and solar eclipses, when the moon blocks the sun. And finally, we will understand how astronomers can predict exactly when these amazing events will happen. Here's a quick overview of what we will cover. First, we will look at the moon's monthly cycle of phases from new moon to full moon and back again. Then we will dive into the science of eclipses, starting with lunar and then solar. And we will end by looking at how astronomers use geometry and timing to predict when and where eclipses will happen. Let's begin with something we all can observe, the changing appearance of the moon. Call its phases. So these changes follow a regular pattern that repeats each month. Even though we always see the same side of the moon, it appears differently each night because the sun shines on it from different angles as the moon moves in its orbit. So these phases form a consistent cycle, starting from a thin crescent, growing to full, and then shrinking back to crescent again, roughly every 29 and a half days. So you can try this yourself. Look at the moon at the same time each evening, and you will see it slowly shift shape and position in the sky. So this figure shows actual images of the moon taken each day. You can see the pattern of growing and shrinking light clearly. So these visible changes, the phases, are connected to how the moon moves in space, which we will dive into next. Now let's look at how the moon's motion causes the phases we just saw. The moon is constantly moving around Earth and quite fast. So if you could float above Earth's north pole, you would see the moon orbiting in a counterclockwise direction, the same as Earth's motion around the sun. And the moon's orbit is tilted about 5 degrees from Earth's path around the sun. So that's why it is usually a bit above or below the sun in the sky, which also explains why eclipses don't happen every month. And the moon shifts about 13 degrees to the east every day, so it rises and sets about 50 minutes later each night. So if you watch it for an hour, you can actually see it moves a bit against the background stars. Remember, the moon rises about 50 minutes later each day. Now, the phases we see are just sunlight hitting the moon from different angles. So the moon shadow is not involved. That only happens during eclipses. Now that you know how the moon moves and why it changes appearance, we are ready to explore exactly what those phases are and how they line up in the moon's orbit. So in the last slide, we saw how the moon orbits Earth and moves eastward each night. But here's something even cooler. Even though it moves around Earth, we always see the same side of the moon. How is that possible? The moon rotates once on its axis every orbit it completes around Earth. So that means moon's rotation period and orbital period are same. So this is called synchronous rotation. It's like the moon is dancing around Earth, always keeping one face towards us, like something walking in a circle but always staring at you. That's why we only ever see the near side of the moon, with the same familiar mountains, craters, and those dark patches we call Maria. The far side stayed a mystery until spacecraft photographed it. So we just learned the moon always keep one face toward Earth. But that face doesn't always look the same. Why? Let's find out by looking at the moon's changing shape. So no matter where the moon is in space, sunlight always lights up half of it. There's always a lit side and a dark side, just like a basketball held under a lamp. Alright, let's look at this image. Can you all see how the sunlight is coming in from just one side? Now notice how only half of the moon is ever lit up by the sun, no matter where the moon is in its orbit. Now let me ask you, if the sunlight always hits one half of the moon, why do we see it change shape? As the moon orbits Earth, the angle between the sun, moon and Earth changes. So we are just seeing different portion of the sunlit half from our viewpoint on Earth. So remember, the moon doesn't create its own light and it's always half lit. The faces we see just depends on where it is in its orbit. So the trick is, as the moon orbits Earth, we see different amounts of that lit side, and that's what creates the faces. Now let's walk through what those changes actually look like, starting with the first 2 weeks of the cycle, the waxing moon. So let's look at what the moon is doing during the first 2 weeks of its cycle, what we call the waxing phases. So the word waxing means growing, like waxing poetic or waxing strong. So each day we see more of the lit side as the moon moves away from the sun in the sky. And these waxing phases are visible in the evening. So if you look toward the west after sunset, you will see the moon slowly climbing higher and getting brighter night by night. Now notice how the moon starts off right after the new moon, barely visible, and slowly grows each evening. So you will see it mostly in the evening sky, just after sunset. So let's try this. Next time you are outside in the evening, look toward the western sky and see if you can find that waxing crescent or first quarter moon. Now here's a question for you. When it is a waxing gibbous moon, are we getting close to full moon or far from it? Yep. Waxing gibbous means we are almost there. Then comes the full moon. But after that, the process reverses. So let's explore the second half of the cycle, the waning phases. Now let's follow the moon during the second half of its cycle, the waning phases, when it gets smaller and heads back towards new. So waning means decreasing. After the full moon, we start to see less and less of the illuminated side until we return to new moon. And the cycle starts again. So unlike waxing phases, waning phases are best seen at sunrise. If you are an early bird, you will spot the moon slowly fading and shifting closer to the sun each morning. So let me ask, have you ever seen a skinny crescent moon early in the morning and wondered why it's up at that time? That's waning crescent, getting ready to go back to new moon. So from full moon to new moon, the moon is rising later and later until it's back near the sun and basically invisible. So that's the full story of how the moon changes. Not because it changed shape, but because our view of its lit side changes as it orbits Earth. So let's imagine we are watching the stars every night and tracking the moon against them. It takes 27.3 days for the moon to come back to the same spot among the stars. That's called the sidereal period. So try to picture this like the moon making a lap around a running track, but using stars as the lane markers. Now what about the cycle of the moon's phases? You know, from crescent to full moon and back. That takes 29.5 days. It's called the synodic period. So why is it longer than the sidereal one? Because while the moon is orbiting us, Earth is also moving around the sun. So the moon has to catch up to realign with the sun. Think of it like trying to catch someone on a moving walkway. Now let's take a look at this image. You can see two different parts here. One shows how the moon returns to the same position relative to the stars, sidereal, and the other shows how long it takes for the same phase to come back, synodic. Okay, so now we understand how long it takes the moon to orbit and cycle through its phases. But what about those myths we often hear about the moon? Let's bust a few of them in the next slide. Here's a cool fact. The word month actually comes from month. That's because ancient cultures used the moon's 29.5-day cycle to measure time. So when you say next month, you are echoing ancient astronomy. Now let's also clear up a few moon myths. You have probably heard people say the dark side of the moon, maybe even in movies, but guess what? There's no part of the moon that's always dark. Every part gets about 2 weeks of sunlight, then 2 weeks of darkness. It's just that we always see the same side from Earth. Second, how many of you have ever seen the moon during the day and thought, wait, is that supposed to be there? It is, especially when it's in its crescent, quarter and gibbous phases. The bright sky makes it harder to see, but it's totally normal. I never heard someone say that people act wild during a full moon. Sorry, werewolves, science says otherwise. Studies of hospital records, crime stats, and schools show no actual increase in unusual behavior. It's just a myth. So next time someone talks about the dark side or blames the moon for their behavior, you can be the expert and set the record straight. Next, it's humbling to think the moon we see today is the same one seen by ancient humans, early civilizations, and even dinosaurs. That glowing face in the sky has inspired myths, calendars, poems, and science for thousands of years. Alright, now that we have explored how the moon moves and how we see it, we are ready to look at something even more dramatic. What happens when the Earth gets between the moon and the sun? Let's dive into lunar eclipses next. Okay, we just talked about the phases and how the same phase of the moon always looks at us. But once in a while, something dramatic happens. The moon seems to vanish or turn red. Let's explore why that happens. Okay, a first quiz for you. What's the only moon phase where Earth could block sunlight from reaching moon? Check this image. Yes, the full moon. That's the only time lunar eclipses are even possible. Here's something that trips people up. We get a full moon every month, right? So why not an eclipse every month? Well, the moon's orbit is tilted. So most of the time it misses Earth's shadow. Now imagine Earth as a giant umbrella blocking the sun. If the moon walks into that shadow, boom, we see an eclipse. But it has to line up perfectly for that to happen. So check this out. This diagram shows why eclipses don't happen all the time. Most of the time, the moon takes a path that misses Earth's shadow. Only when everything lines up just right, we get that spooky red eclipse. So now we know that eclipses are all about alignment, and they are rare because the moon's orbit is tilted. But let's dig deeper into Earth's shadow and how it causes the moon to go dark in the first place. First, let's take what we just learned about shadows and bring it into the real world. You don't need a telescope, just a lamp and a ball. So this is the one of the best ways to actually see how shadows work. A simple light bulb setup lets you explore the same physics happening out in the space. So let's break it down visually. The light bulb is like the sun, and the ball is Earth, and the screen catches the shadow like the moon would. Now notice how the shadow has a darker inner core and a fuzzy, lighter edge. That's the umbra and penumbra. And this is exactly what happens during a lunar eclipse. So if you look closely, the screen behind the ball shows a very sharp dark shadow in the middle. That's our umbra. Around it is a lighter, blurrier zone, and that's penumbra. So when the moon enters that dark part, it turns red and dim. So depending on where the moon falls in Earth's shadow, full dark, half dark, or just slightly dim, we get different kinds of lunar eclipses. You could try this at home with a flashlight and a ping pong ball. So next time you see the moon turning red, just remember it's drifting into the deepest part of Earth's shadow. And now you have seen how that shadow works. Now let's walk through what actually happens when you watch a total lunar eclipse from beginning to end. First, let's take a close look at this diagram A. This is a map of total lunar eclipse. You can see the moon is moving from right to left, passing through Earth's shadow. So the grey outer ring is called penumbra, where only part of the sunlight is blocked. And the dark central part is the umbra, where all direct sunlight is blocked. Now notice how the moon starts outside the penumbra and then enters the penumbra, just dimming a little at first and finally sides into the umbra, where it gets really dark. If you're standing on Earth watching this happen, you would see the moon slowly fade and then suddenly start turning red as it dives into umbra. And guess what? The moon doesn't glow by itself. What we are seeing here is just the effect of Earth's shadow moving across the moon. Now let's get into the facts. Again here, the moon slowly fades as it moves into a shadow. At first it looks like nothing much is happening. It just gets a little dim. But then suddenly a dark curve starts creeping across it. And that's Earth's umbra. And now we are watching a real lunar eclipse unfold. So the moon doesn't just flick off like a light switch. It slowly moves through shadows. First into the penumbra, then the deep umbra, then back out. The entire eclipse can last as long as your school day. Now figure B shows the moon moving right to left through umbra. Notice how it is brighter on one side and reddish in the middle. That's real, not Photoshop. Now that you know the stages, let's figure out why the moon turns red instead of going completely dark. Now have you ever seen a red moon and thought it looked like Erie? It's not magic, it's Earth's atmosphere at work. So let's look at how red the moon is here. But also notice one edge is brighter, and that side was closer to the edge of the umbra. So if you're standing on the moon during the eclipse, Earth would completely block the sun, but you would still see a reddish glow, a ring of all the sunsets and sunrises happening on Earth at that moment. So that red light bends into the shadow and lights up the moon. Sometimes the moon looks bright orange. Other times it's spooky dark red or even grayish. Why? It depends on how much dust and clouds cover Earth's atmosphere has. So every eclipse is a little surprise. Now let me ask you this. What do you think would happen if the moon went straight through the middle of Earth's darkest shadow, the umbra? It is darker and it lasts longer. That because the center of the umbra is the deepest part of the shadow. So the moon spends more time in the darkest region. So some of the longest total eclipses happen this way, up to almost 2 hours in totality. So next time you see the moon glowing red, you are really seeing Earth's shadow colored by a ring full of sunsets and sunrises happening all around the world. Now here's a quick check. Who has seen an eclipse before? Let's explore the ones that often fly under the radar, partial and penumbral eclipses. Sometimes the moon only dips its toes into the darkest part of Earth's shadow. That's a partial lunar eclipse. You will see part of it darken while the rest remains bright. This one is super subtle. In a penumbral eclipse, the moon passes through Earth's lighter shadow. Most people don't even notice it unless they are paying really close attention. You might not see that cool red glow like you would during a total eclipse because the bright part of the moon can overwhelm the shadowed area. Even though they are not as dramatic, partial and penumbral eclipses are still amazing and easy to spot if you know when to look. Alright, now that we know what types exist, let's check out when and where you can actually see them. So this table gives you a decade's worth of lunar eclipses info. Want to watch one? Just check the date and see if it is visible where you live. Lunar eclipses are global. If it is night time where you are and an eclipse is happening, you are in luck. Now we have seen how Earth casts its shadow on the moon. But what happens when the moon blocks the sun? Stay tuned. We are diving into solar eclipses in the next section.